Hi there, we'll continue, oops, we continue chapter 11, of course, with 11.4, the comparison tests. We have two comparison tests. One is called direct comparison test, and the other one is called limit comparison test. So let's look at and see, of course, these are tests for convergence or divergence of series. Okay, so the preliminaries for these tests, number one, we have a series that we are interested in, and another series that we will be using for the direct or the limit, depending on what we are trying to do, which one we want to apply. So these are supposed to be and have to be a series with positive terms. Good. So what does the direct comparison test say? Well, it says that if we have this relationship between the nth terms, right, of these two series, and this big one, the series of Bn, Sn equals 1 to infinity, of Bn is convergent by the direct comparison test, this one, the smaller one, n equals 1 to infinity, from a sub n is also convergent. Also, the direct comparison test says this: if I have this relationship, and notice that it's not the same, it's the opposite, and the small one, okay, n equals 1 to infinity from Bn is divergent, so is, by the direct comparison test, so is the sum, the infinite series, is divergent as well. Notice one thing here, that if we have this relationship and this one is divergent, so if the big one is divergent, we cannot conclude anything about the small one. Do not conclude anything about the small one. So if the big one is convergent, the smaller is convergent. If the small one is divergent, then the big one is divergent. But if the big one is divergent, we cannot conclude anything about the small one. So careful on that. Now let's look at the limit comparison test. The limit comparison test says this. Of course, the same conditions. We have two series and they have positive terms. Okay, same conditions apply here. If the limit of an over bn as n approaches infinity is a number finite and greater than 0, not 0, then by the limit comparison test, both are either both divergent or convergent. So that's what the limit comparison test states. Okay. Now also one item here about estimating sums. And the preliminary or the requirements here are, number one, again, positive terms, of course. Number 2, we know that this series is convergent. Then for, as you remember, Rn is the remainder. So this will be S minus Sn, and of course these are n plus 1, a of n plus a n plus 1 plus a n plus 2, and so on and so forth. So this comes from a sub n. But we also have the other series, Bn, and we have to differentiate between the two, so we are going to denote the remainder for this series when we approximate with a particular n partial sum. So this is by t minus tn, and this of course is t n plus 1, of course b, b n plus 2, and so on and so forth. And in this condition, in this situation, always this, by comparison, will always be less than this. So the remainder for a sub n, the first series, and the one we compare to, or we use the limit for, to apply the limit comparison test, this will always be true. Okay. So now let's look at a few examples. So at page 3. So let's look at 7 on 764. The question is asking us determine whether the series converges or diverges. And we have n equals 1 through infinity, 1 over n cubed plus 8. This is a simple situation because 1 over n cubed plus 8, because the denominator is bigger here, this will always be less than or equal to 1 over n cubed, which we know this is a p series with, so 1 over n to p, so n approaches 1 from 1 to infinity. So this is the p series. In this case, p equals 3, which is convergent. And we know that a p series is convergent as long as p is greater than 1. So therefore, by the direct comparison test, we conclude that n equals 1 through infinity, 1 over n cubed plus 8 is also convergent. Okay, next, problem number 9, same page. And we have the sum, n plus 1, and the square root of n, as n goes from 1 to infinity. Okay, the same idea here. We have n plus 1 and the square root of n. And we know for sure that this is greater than or equal to, if I remove 1 from the top, this fraction will be smaller than what we had originally. If we simplify this, we get 1 over n to 1/2. But this time, this is a p series with p 1/2. So then this, we know it's divergent because p is not greater than 1, so it's less than 1. So therefore, by the direct comparison test, the sum from n equals 1 through infinity from n plus 1 over n, the square root of n, is also divergent. Okay, let's continue with 11 on 764. What does 11 say? Yes. So we have the sum 9 to the n, 3 plus 10 to the n. Again, a simple situation if we remember the geometric series, because 9 to n over 3 plus 10 to n, I'm minimizing the denominator, removing the 3. So then this has to be less than or equal to 9 over 10 to the nth power. This is bigger because it has a smaller denominator. But this is geometric with the common ratio 9/10. So as long as the absolute value is less than 1, then we are safe. In other words, this is convergent. Therefore, the initial series is convergent by the direct comparison test. We always have to write why. So page 4. So therefore, this original series is convergent by the direct comparison test. Okay, next one, 19. On the same page, 764. Let's see, 19, yes. 4 to n plus 1 over 3 to the n minus 2, n equals 1 to infinity. Good. So in this situation, again, let's take a look at 4 to the n plus 1 over 3 to the n minus 2. And realize that, again, if I increase the denominator, this will be greater than or equal to, because I'm removing the negative 2. So this will be greater than or equal to the 4 to n plus 1 over 3 to the n. This one will be larger because the denominator is smaller than this one. So then this becomes 4 over 3 to the nth power, which is geometric. But this time, the common ratio is 4/3. So therefore, this is divergent. So if the bigger one, if the smaller one is divergent, the bigger one will be divergent as well. So from here, we have that the original series is divergent by the direct comparison test. Moving on to 21, still on page 764. And here we have the sum from, n equals 1 to infinity, of course. And this is 1 over the square root of n squared plus 1. Good. So in this particular case, looking at this series, this generic term an, and remembering that we talked about this as being harmonic and divergent. So this is our a sub n, and this is our b sub n. So let's take a look at the limit comparison test this time and see what we get. So the limit as n approaches infinity, a sub n has to be at the top, and b sub n has to be in the denominator. So this is limit as n approaches infinity, n over the square root of n squared plus 1. I know the book says to multiply top and bottom or divide top and bottom. I don't like to do that. It's up to you. I prefer to factor, because if you do that and this approaches negative infinity, the whole thing collapses. So what the book is showing is specific for a particular type of problems, but not for all. What I'm showing you is always true for all of them. So factor out the degree, which is 2, which is n squared. So 1 plus 1 over n squared. And now this square root of n squared, because it's a product, I can separate. So let me write one more step. This should be the absolute value of n times the square root of 1 plus 1 over n squared. But there is no need for the absolute value because n approaches infinity. So then I will eventually simplify. And the answer will be, this approaches 0, so the answer is 1. which is a finite number, it is greater than 0. Therefore, by the limit comparison test, both knowingly that this series, the harmonic series, is divergent, both of them will be divergent as long as this number exists, is finite, is greater than 0. So then by the limit comparison test, we conclude that the original series, n equals 1 to infinity, from 1 over the square root of n squared plus 1 is divergent by the limit comparison test. Okay, moving on. 23. Same page, 764. Let's see how we are on time. Close. Okay, 23. So we have the sum, n equals 1 to infinity, n plus 1, n cubed plus n. So we're looking at this situation, and I see n over n cubed, which is the series that we can compare with using the limit comparison test, n equals 1 to infinity, which we know it's a p-series, with n equals 2, which we know is convergent. So let's look now at the limit as n approaches infinity. Always a sub n first, and the denominator 1 over n squared. Remember, we have to flip the denominator, so we have limit n approaches infinity. So we have n cubed plus n squared over n cubed plus n. And yes, what I just did a second ago, a few minutes ago, I will factor out the degree, or you consider that you apply the L'Hopital's rule, whatever you want to do. Both are fine. In this case, I prefer just factoring out n cubed. So n cubed, and this is 1 plus 1 over n, and n cubed 1 plus 1 over n squared. And the limit is 1, is greater than 0. So therefore, both converge, or are convergent, better, by the limit comparison test. Good. We want to look at 3 more, so I'm going to continue with the next video.